Hello, in this lecture I want to fit a one-way ANOVA using systolic blood pressure data. So typically when we want to test the hypothesis of equality of the mean for more than two groups, we will use an ANOVA test, okay? So to fit the one-way ANOVA, there are some libraries that we will use from Stat Model. And let's get started here by importing all that we will need and then reading the data frame to then discuss how we will fit the ANOVA to the data. So the first one I want to import is statmodel.api as SM. This will be used for checking the residual to see if the residual are normally distributed. All right. Then I will import statmodel.formula.api as SMF. Okay. That along with the other stat model import will be used to fit the ANOVA table, print the table, as well as like stat model.stat.multicomp. This one will be used for the two key HSD. So let's import them, and as we are fitting each aspect of the model, it will be clear as to what each import does. Here we have the pandas and numpy that we bring in all the time, either to read in the data or to do some computation. And finally, I'll import matplotlib and seaborn graphical libraries to be able to construct Boxplot to see how the group means distribute. So let's import the libraries. When we are using them, then we will reference back to the import. All right, so we have here two columns. The first one is treatment, and the second one is blood pressure. So we have the question that we want to answer here: is the mean blood pressure the same for medication, exercise, and diet? Okay, if they are not the same, then we want to know which of the group mean differs. So as you can see, this is a typical one-way ANOVA test. All right, we have more than two groups. In fact, we have three groups: medication, exercise, and diet. So this is an ANOVA test. If we had only two groups, let's say medication, exercise, and we want to know if the mean blood pressure differ for the two treatment type, then we will use a student T. But here we have three groups, we need to use a one-way ANOVA. How do we fit the ANOVA? So we imported statmodel.formula.api as SMF, so we will use SMF.OLS, and here we have a single quote: the blood pressure is the response variable. All right, then tilde. Notice I'm using the C. In this particular case, since the treatment are categorical or text, it does not matter. I can omit the C and the parentheses. But let's suppose that the treatment were numerical. So let's say 1 for medication, 2 for exercise, and 3 for diet. If we want the model to treat it appropriately, like 3 categories, we use C for categorical and then parentheses treatment, right? Then we treat them as text. Okay, so response variable tilde C treatment parentheses, we close the quote, and then we pass it the data frame df, and finally that fit. And to obtain the ANOVA table that fit the model, to obtain the ANOVA table, we use the ANOVA_LM. So ANOVA_LM is imported from statmodel.stat.ANOVA. Okay, so we use the ANOVA_LM, the model, and type equal to. Type equal to simply says that print the model but without intercept, and then type equal 3 it will list the intercept. I'll run it without the intercept with type equal 2, and then we will run it with type equal 3 to show the intercept. Okay, let's print the ANOVA table. So you can see we have the treatment. All right, there are 3 groups. So the degrees of freedom will be 3 minus 1 or 2. Then we have the residual, the error. Notice that the model is significant. P-value is 0.003831. All right, so there are significant differences in treatment. All right, suppose then I use a type equal 3. We cannot use type equal 1. It's 2 or 3. So if we use a type equal 3, now notice it's printing the intercept. We don't need that. So there are cases where you may want to use a model with intercept, but in this particular exercise, I don't. So I'll go back to type equal 2. Now we know that our model is significant, so there is a significant difference in treatment. All right? So since there's significant difference in treatment, we want to know which one significantly differs. For example, is it medication and exercise, or medication diet, or exercise diet? We want to know which one is significantly different. In order to know that, we will do a multiple comparison. This is called a 2-key multiple comparison. So we will run the 2-key multiple comparison. And the way we do that, from start model.start.multi-comp, I'm importing this as multi. So then I will use, I call it MC treatment equal multi-comparison. I pass it to 2 columns. One is the response variable and the other one is the treatment. All right. And after I run the multi comparison, I need to run the 2-key HSD. So I say result underscore treatment equal MC treatment that 2-key HSD. The 2-key HSD will do the multiple comparison test, and here I'm printing the result. Let's do that. So the family-wise error rate is 0.05. Okay, this is the default. No need to change that. So here's how the test is run. You know, we have group 1 and group 2. So in group 1, we have diet and exercise. You see, they are not significantly different. All right. This is the confidence interval. The confidence interval is minus 878.39 to 1.1839. So notice that this includes 0, which implies that it's not significantly different. But the result of the test is here, where the false means that it's not significantly different. So diet and medication, not significantly different either. So you see, false. Now, exercise and medication, so the mean blood pressure for those who exercise and those who take medication only, there is a significant difference. So it's set to 2. Okay? All right. So the ANOVA is significant. We went through the 2-key test and we found out which groups are significantly different and which one aren't. But it's always good to visually depict the data so that people can visually see whether there is a difference in the mean blood pressure of the groups. One way to do that is using the box plot. Okay? So to construct the box plot, here I start with just setting up the basic box plot chart layout for the font and the graphical display. So typically I'm using a font size of 16 for the label size, the title, and any font size at all. And then in Seaborn, I set the context to paper. It's just a display or a theme I could set it to notebook. This is just for controlling the look of the chart. All right, so I say plt.title. I give it a title. Boxplot comparing blood pressure by treatment type. Then this is the most important, where I'm running the Boxplot from Seaborn SNS.Boxplot. The X variable is treatment, and the Y variable is the blood pressure. Okay, so I need to pass in X and Y, and then specify the data frame. Then pass it the label for the X-axis, X label for the Y-axis, Y label, and then the ticks, I just rotate them to 45 degrees. Now let's display this. This is how it looks like. All right, so in our tests, it said that exercise and medication are significantly different. So the mean blood pressure for people, for those who exercise and those take medication, is significantly different. So you can see through with the box plot, this is medication, this is exercise. All right. So you see, medication only, the mean blood pressure is high. All right. The box plot, the distribution of the box plot is higher than that of exercise. So those who are in the exercise group have significantly lower blood pressure, right? They don't overlap at all. Now, if we look at exercise and diet, we see some overlap. That's why the test did not find exercise and diet to be significantly different. See, exercise, diet, they are not significantly different. How about exercise and medication? Again, the test didn't find those two to be significantly different. But when you look at medication, exercise tend to lower the blood pressure compared to just the medication. So the box plot is a good way to support the result of the ANOVA and the Tukey test. Okay. All right. Now that we did that, we need to just do some quick model diagnostic. The first one is check to see if the residuals are normally distributed, because that's one assumption of the ANOVA. Okay. All right. So here we are using the SM. So we're importing SM. Let's go back. From start model.api we import it as SM. So we are using QQplot under that library. So first we obtain the residual from the model. So we say model.resid, return the residual, and the figure that we want to plot is sm.QQplot. We want to do a QQplot of the residual, and then use an S symbol for the line. Let's do that. All right, so you can then see that these blue points are approximately lined up, you know, on the red line. So there's not much distortion. Okay, so we can say that the residual are approximately normally distributed. Right? Then another assumption is equality of variance. So we can do equality of variance by testing to see if the variance for those who take medication, exercise, and diet are the same versus the fact that they are different. So what I'm doing here is just obtaining the medication column, the exercise column, and the diet. So I said DF, that blood pressure, treatment equal medication. All right. So for exercise, same thing, blood pressure, DF, treatment equal exercise. And finally diet, the same thing. So to sort of extract the column for each variable. Once I did that, then I can use the leave-in test within SciPy start to test to see if the variances of these three groups are the same. So the leave-in test requires that we specify the columns for which we want to test equality of variance, and it will return the test statistic and a p-value. All right, and here I'm printing the test statistic and the p-value. Let's run this. Okay, so the p-value is 0.878. So at 0.05 level of significance, the p-value is greater than 0.05, which means we cannot reject the null hypothesis that the variance of those in the medication, exercise, and diet are the same. So overall, the model holds. The variance are about the same. The variance are the same. Okay, and here the residual are approximately normally distributed. All right, and our box plot tend to go along or confirm what we are seeing here in the Tukey HSD. So this is how we run a one-way ANOVA. Now, I mentioned here that if we didn't use the C, since the treatment is categorical, it's text-oriented, it wouldn't matter. Let's remove it and run it. See, we're still gonna get see, still get treatment, same degrees of freedom, same p-value. That's because this is already a text or character, so we don't need the C. But in some instances, this treatment may be categories like 1, 2, 3, some numbers. So in this case, we would need to use the C like that. This is saying treat this as a category. All right, thank you.